Hello, we are Team Astra Robotics, a multidisciplinary student club from RV College of Engineering, Bangalore. We are proud to present our rover Tara for this year's URC. We are a group of 20 students working passionately to build the next Mars rover.
Mechanical design, starting off with the chassis, we've opted for a lightweight yet robust space frame design using aluminum extrusions. This allows for modularity while keeping the weight low, helping us to stay within the stitch weight limit. The frame is designed for easy assembly and maintenance, making quick adjustments in the field much easier. At the heart of the drivetrain, we have an open air differential system which allows torque distribution while maintaining a stable drive. For wheels, we're using off-road treads optimized for rocky and sandy terrain.
This year's robotic arm has 5 degrees of freedom, and we have made use of aluminum extrusions to significantly reduce the weight, bringing it down to 8 kgs. The base, elbow and shoulder joints make use of planetary geared DC motors, and the rest uses continuous servo motors. The base joint has a spur gear reduction. The elbow and shoulder have cycloidal gearboxes integrated into the joint. The cycloidal gearbox has a reduction of 19:1 and is a fusion of 3D printing and aluminum laser cuts. It has been designed from scratch and fabricated completely in-house. The gearbox can produce a maximum torque of 100 Nm. The arm extends up to 1.2 meters from the base to the end effector and can lift weights up to 7 kgs. The rest uses a bevel gear differential mechanism, adding 2 degrees of freedom to the configuration. The gripper is based on lead screw mechanism for the movement and is designed to exert large clamping force.
This year, our rover is powered by a pair of 12-volt LiPo batteries and a custom battery pack made from 42 lithium-ion cells in a 14P3S configuration. A custom battery management system with passive cell balancing and monitoring of body temperatures, coulomb counting SOC and SOH is used. On our custom power distribution board, we boost our voltage to 24 volts to power the antenna and buck our voltage to 5 volts and 11 volts to power our embedded system.
Our control system on all MCUs communicate with ROS using micro-ROS framework. We use FreeRTOS for efficient task scheduling and handling priority when running multiple processes concurrently, such as reading sensor data, controlling actuators, and for communication stack. A PID-based controller is employed by using feedback from IMU to maintain constant velocity when rover traverses steep slopes. For the robotic arm, we made use of absolute position encoders at each joint and an IMU at wrist joint.
Kill switch is employed to shut off power to all the systems in the rover.
Communication between base station and rover takes place over 2.4 GHz using TP-Link CP210 directional antennas, ensuring strong connection and over 1 km of range in LOS conditions. Commands are published to ROS topics which control the drive and arm. DDS was configured to ensure security and speed over the ROS network. Multiple camera feeds are sent back by the rover to the base station using WebSockets, ensuring low latency. A steering mechanism is implemented on the rover which uses the filtered IMU and encoder data to calibrate the antenna at all times.
The entire navigation stack is built on ROS2 with Nav2 as the core framework. For precise location, we have used a dual GPS system with one unit at the base station and another on the rover. This is combined with the data from the IMU and visual odometry from the Z2 camera, all of which are fused using extended Kalman filter to achieve highly accurate positioning.
For the navigation mission, the GPS waypoint follower acts as the global planner, which ensures that the rover follows the designated GNSS coordinates with precise heading control. At the same time, a local cost map is generated by using RTAB map as the framework for SLAM, which uses LiDAR and Z2 camera for point cloud data, enabling real-time obstacle avoidance during traversal. Once the rover reaches its target coordinates, it initiates a hexagonal search pattern to detect Aruko markers.
This year's Life Sciences module, we are conducting 4 experiments to detect the presence of extinct and extant life in the soil surface. The Bradford's test is used to detect the presence of proteins in the sample. The Safranin dye test is used to stain and identify microbial communities in the sample. The hydrogen peroxide test is used to detect the presence of organic matter in the sample. The carbonate test is used to detect the presence of carbonates and bicarbonates, which indicate the presence of biological activity. We have designed a soil sample caching system, which uses an auger to drill with a lead screw conveyor to deliver and distribute the soil into test tubes without cross-contamination to conduct on-board tests.
Our team this year decided to completely redefine our strategy in tackling the URC missions. We decided to have only one mission in mind, to have a functional modular rover that's capable of tackling all the URC missions. As student engineers, we strive not only to create a rover that is competition ready, but also which proves to be a testament for our passion and innovation in robotics.